Hello, everyone. Welcome to week 4. We are talking today about independence. So, for a little bit of context, we've covered some parts of probability theory. We've defined probability and defined also the concept of a distribution or a density function that lets us describe population instead of by kind of enumerating all of the individuals in that population by just describing kind of qualitatively roughly speaking, the histogram that the variables in that population take. And today we're going to build on that and talk about this idea of independence, which helps us describe the relationship between different variables that are measured on individuals in a population. So in particular, we're going to formalize what we mean by when variables are not related to each other in some statistical sense. So let's get right into it. The idea that we're trying to formalize or capture is that sometimes when you know one variable, that can help you guess the value of another variable, and sometimes it can't. So, for example, if I flip a coin and I see that it comes up heads, does that help me guess who will get the flu? Let's say people in Berkeley. Who in Berkeley will get the flu next season? And the answer intuitively is no. So another question, if I know who's vaccinated, can that help me guess who will get the flu next season? And the answer, I think, for that one should be yes. And the last one, if I know a person just won the lottery, can that help me guess whether or not they went to college? So here I'm emphasizing that we're not always necessarily predicting forward in time. We're just saying, if I know something about a person, is it more or less likely that something else is true? And for this one, the answer is actually yes, and we'll get to that in a second, which may be surprising. So let's say here, let's do a quick amount of review. We have this idea of a marginal probability, which is just a population proportion, right? So here, if I'm asking in the U.S. population, what's the probability of college equal to 1? That's just the proportion of people that went to college. But you can think of this also not necessarily not as a proportion, but as like your a way to guess, right? So if I pick a random person, will they have a college degree? If I pick a random person, 37% of random people will have that college degree. And so, my guess as to whether or not somebody has a college degree, if I pick them at random, I'd have to guess no, right? I'd be more likely to, if I'm winning $1, if I guess correctly, I want to guess no. I'm more likely to win that dollar that way because less than 50% of people have gone to college. So the best I can do in this scenario is to guess no, because if all I know is that we're picking at random from the US population. However, if I change the problem and I talk about instead not the population at large, but a subpopulation, so I'm stratifying to just people who have a high school degree. And now I ask you the same question. Well, the game changes because you may know that among high school graduates, actually a little over 50% do go to college. So now you want to guess yes. So by giving you this additional information of that I'm only picking among people who went to high school, the probability of college has changed, and your kind of best guess as to whether or not this random person went to college should be different. So the idea is this, that if you know a particular variable, in this case high school, has a certain value, if that changes the probability of another variable, then we say that those two things are statistically dependent. So in this case, the event going to college is statistically dependent on the event having graduated high school, because the marginal probability is not the same as the conditional probability. In other words, knowing the high school gives you information about the value of the college variable. So that's what's basically said here, that it helps me guess if I know one thing. And formally, the idea is just that these marginal and conditional probabilities are different. Another way to look at this, I'm just trying to give you kind of many different views of the same thing, right? Another way to look at this is that the probability varies within subpopulations. So the probability in the larger population, in this case, is 37%. In the subpopulation of people with high school degrees, it's 52%. So those are different. So if the probability of a variable is different among subpopulations, then that variable is dependent on whatever variable is defining the subpopulation, in this case, high school. That's dependence. We can talk also about independence. Independence is when the marginal and conditional probabilities are equal. So this is the case, let's say I have everybody in the US flip a coin, and I'm asking about what's the proportion of people who went to college? Still 37%. Now I say among people who got heads in their coin flip, what's the proportion of people who out of those who went to college? It should be 37%, because that coin flip has nothing to do with whether or not they went to college. They're going to get roughly the same amount of people who go to college or don't are going to get heads or tails. So that should be the same. So these variables we would say are independent. Or strictly speaking, these events, college equals 1, heads equals 1, are independent. More generally, when we have variables, random variables x and y, we say that the marginal and conditional probabilities are equal. When the marginal and conditional probabilities are equal in this way, we say that those two variables are independent from each other. And implicitly here, we're talking about for all values little x, little y, or for all possible sets that x can live in or that y can live in. So for example, here I'm talking about college equals 1, heads equals 1, but for the random variables to be independent and not just the events, this would have to be true for college equals 0, for heads equals 0, for college equals 0, heads equals 1, for all possible combinations, and for all possible sets. So if this were a variable like age, that could take values, let's say 0, 1, 2, 3, 4, 5, then whatever, I could say age is less than 2, given heads equals 1. Any possible combination of some condition here on age and some condition here on heads, this would have to hold. So basically, no matter how you slice things, you get the same marginal and conditional probabilities. If that's the case, then we say those random variables are independent. So again, the idea is that if they are independent, then the variable x has the same distribution among all different strata of y. That's essentially what this means. So if you think of this as the distribution of x in the general population, and you think of this as the distribution of x in some stratum defined by y, all we're saying is that the distribution doesn't change when you stratify. And if you are thinking of probabilities as like ratios of counts where things are happening relative to some larger population, this marginal probability of x is just how many times does x happen relative to the total number in the population. And over here, the conditional probability, right, is how many times does x happen at the same time that y is happening relative to the total number of times that just y is happening. So this is like the subpopulation proportion. And maybe we can think about it very concretely in terms of like, pink people and the black people, and some people are wearing hats and some people aren't. So this is the case where hat wearing is independent from what color person you are. Why is that? Because you can see if I stratify the population in terms of what color these people are, 1/4 of the pink people are wearing hats and 1/4 of the black people are wearing hats. So we have 2 out of 8, 1 out of 4. That's the same proportion, right? You can also split it the other way. You can say among hat wearing, if you stratify by hat wearing, we have here 1-to-2 ratio of pink to black, and same over here, 1-to-2 ratio of pink to black. So you can kind of think of these two variables as creating this like, kind of table where the lines are perpendicular to each other if you're kind of counting things this way. And you might imagine, okay, what about a distribution where a joint distribution where things are not independent, where there's dependence? Well, that could be something like this, where like if this person were wearing a hat, right? Now you see that the ratio of hat in the pink people, you still have 1-to-4, but down here you have 3-to-8, right? So those two ratios are not the same. You can think of this kind of dividing line as being crooked in a way. This isn't formal. I'm just trying to give you some kind of intuition as to like, if you have variables that are independent, you can maybe imagine putting people in a grid, and then how would those kind of grid lines look? How would the ratios of people look? Just to give you some intuition. So let's back up a little bit and just think of it conceptually about these problems. So let's say you give everyone in a population the same 2 coins, and you ask them to flip them each once, and you record the results. And the question is, are the random variables that represent the 2 coin flips independent? So you might say yes pretty immediately, but let us just kind of think about it a little bit. So here, let's say I'm going to make like the data table. So this is often helpful to do. Always kind of think about your data in terms of this, like, population data set, right? So we have, here are our people in the population, 1, 2, 3, 4, 5, so on and so on, right? Up to some really big number, who knows? And then we have the result of the 2 coins that they flipped. So maybe this guy got 2 tails, and this person, got a heads and a tail, and this person got heads, whatever, and so on and so forth. So the question about independence is, if we just look at the marginal distribution of coin 1, what's the proportion of heads? Well, we can expect that to be one half. So this is not really equality. I'm just saying that the marginal probability of coin 1 being heads is about a half. When we ask about then, so if we want to show that these 2 things are independent or dependent, we have to ask whether the probability of, I'll just say, C1 equals heads given coin 2 equals heads, is that the same as the marginal probability? For coin 1. So this, we said it's a fair coin, so it should be about a half. So the question is this 1/2 or not? And it's a conceptual problem. There's not like a way to deduce it here. But conceptually, and what is this? So this is if we just take the rows where this is heads, right? So coin 2 equals heads, and then we get rid of the rows where it's tails, right? So we're going to get some subset of this data frame, which is the subpopulation where coin 2 is heads, and we want to ask, okay, if we just count up the heads and tails in this column for those rows, should it be half? And intuitively, you should imagine that it is, right? Because there's no reason why people who got heads on the second flip should have gotten heads on the first flip, right? These are 2 different coins. Maybe you could argue that some people are like good at flipping heads, or they have a certain preference for like when they flip the coin, they put it face up or face down. And then there's some kind of consistency there. So you could potentially argue that these things are actually not independent, but in a kind of a idealized world, you might think that they are, right? So again, this is just conceptually a question about how do you think about independence? How would you argue that 2 things are or aren't independent? What's the definition of independence? And kind of getting a little bit into the thinking about, well, like really in the real world, it's not always so clean, right? So here's another problem. We have this table. This is a very tiny population, only 6 people, okay? So again, you're never going to see populations like this, or there's really no reason in general that you'd have a imaginary population so small, but this is for the sake of understanding the concepts. So if you had such a tiny population, you have 2 measurements, x and y. Both of these take either value 0 or 1. And you have these missing values here that I haven't given you. And the question is, can you fill these in so that x and y end up being independent in this population? So again, the idea is that you need, if you want this to happen, you need the probability of, you need these things to be the marginal probability to be equal to the conditional probability. And technically you also need, right, this to be the case for all different values that these things can take. So for example, this needs to be the case, and so on and so forth. If I had x equal 1, y equals 0, all of those things need to be equal for x and y as random variables to be independent. And but since they're binary, these things actually imply each other. So if you just have this, then everything else works itself out. And that basically happens because this thing is equal to 1 minus that thing, and you can do the rest of the math if you want to see that is the case. So here, basically, that's what we need to figure out how to do. So I'm just gonna start writing numbers. So let's say I put zeros here and I put ones here. So now what I have is the marginal probability. I've basically set that to be equal to 1/2 because I've put half zeros and half ones. So now all I need to do is make sure that the that's not going to work. Okay, because that's not going to work because I need to set my conditional probability to be equal to 1/2, right? So how can I make that happen? I think that's probably not the best way to do it. So let's say, oh no, I think that's okay. Okay, so let's see what we can do. So here, let's just say that, let's imagine that all these are zeros for now. So right now I already have this being the case, right? Because where y equals 1, we already have the conditional probability as 1/2 because we have 0 and 1. And so 1/2 of these is 1, so we're good, right? And now let's just check that that's also the case for the zeros here if I put all zeros. So now I'm looking at, sorry, right? Yeah, this does work out fine. So now let's just say, looking at the zeros for y. So conditioning on what I'm asking about is the probability x equals 1 given y equals 0. Here we have 2 zeros and 2 ones, so that's also 1/2, right? And of course, that's equal to the probability that x equals 1. And so we're good. So we've done it. So that's all that you need to do. And there's other ways that you could fill this in to accomplish the same thing, where you could maybe have a different marginal probability for x. Like if I had, for example, maybe you should try, is it possible to get this to work out if, for example, we do this, so 0, 1, 1, 1, right? So now the marginal probability of x is no longer 1/2, now it's 2/3, right? So now we need that to be the case among the y. So like for example, we could put a 1 here. And now among the y equals 1 group, we have 2 out of 3 ones, and for the zeros, same thing, 2 out of 3 ones. So that's another way you could fill this in to get this independence, where now x has a different marginal probability. All right, so hopefully the definition is clear enough to you. And how you think about this in terms of a population data set. But I want to point out that the concept of independence, statistical dependence, it has actually nothing to do with causality, even though we might kind of intuitively think about it that way sometimes. So for example, in the coin flip example, we were saying, well, maybe the first coin flip has nothing to do with the second coin flip, right? Like there's no way that it can affect the other coin flip. But then we said, Actually, though, they might still be dependent, because if the coins are both being flipped by the same person, and that person is kind of somehow better at flipping heads or better at flipping tails, then the two outcomes can actually be related to each other, even though one is not causing the other. And so that's a kind of general pattern. And here's another example that may seem slightly counterintuitive to you at first. If it doesn't, great, but I think it's a little counterintuitive. So let's say if you know a person just won the lottery, can that help you guess whether or not they went to college? And maybe intuitively you might think, well, winning the lottery is random, totally random, right? And so how could I know whether or not somebody went to college based on whether they win the lottery? But it's actually not winning the lottery that is telling you something. It's playing the lottery, because in fact, people who play the lottery are less likely to have gone to college. And to win the lottery, you have to have played. So actually winning the lottery tells me that you played the lottery, which actually does tell me something about whether you went to college, even though, of course, winning the lottery by itself is totally random. And doesn't, it's not like it's not like winning the lottery causes these people to not go to college, or vice versa, right? But it's just something about a relationship between these variables, some descriptive relationship, some pattern. That's all we're talking about, right? We're just talking about some pattern in the entries of zeros and ones, or of the different numbers in these two columns in the population data set. It's just a pattern. It has nothing to do with what caused what, or the time ordering of things, or anything like that. And so there's no why when we talk about independence or dependence, even though sometimes when we reason about them, you can try to think of kind of like the causal pathways and say, I can't really think of one, or whatever. You can kind of reason about it that way. But the definition, what we're talking about when we say independence and dependence, there's nothing causal about those things. It's purely the pattern of the numbers in the population data set, roughly speaking.